Hello, everyone. Actually, recording this while I have COVID, so I sound like a weird frog, I think. But anyway, this video is intended to help you with multimass systems using energy as opposed to dynamics. And there's some strategies here, but energy, as per usual, helps this problem be a lot easier. So, we have multimass system here on the right, where you can tell that the 7 kilogram mass is going to fall. And in the past, we had to do a free body diagram for each object, and we had to do the sum of the forces for each, and then we had to isolate the tensions and set them equal. Now here, it's a lot easier. We're going to use energy, but the strategy is, and this will be mentioned again at the end of the video, that you must define a height zero for each object, okay? So, I usually call the lowest point of each object story height zero. Like the 7 kilogram mass is going to fall a distance of 0.5 meters. So I am going to call this height zero for the 7 kilogram mass, and that's going to be 0.5 meters. Now the 3 kilogram mass is going to go up the hill 0.5 meters. Okay, which means that this is height zero for the 3 kilogram mass, its starting point. The height here I would calculate right away as h, remember h equals d sine theta, and in this case that's going to be 0.5 meters times sine of 40 degrees. So I like to do the heights right away. I just kind of like to do that because it's what I like to do. So 0.321 meters. Okay. That's it. All right. So that's step one, is defining a height zero for each. I define the lowest point for each of them as their own height zero. Two separate heights of zero. You don't need to make them the same for both. It's just they're separate objects, do separate heights of zero. After that, you go back to the work energy theorem, except it's going to be long. It's going to be really long. So here we go. Now, you have the kinetic energy. Whoops, we don't want that color. We want that color. You have the kinetic energy initial for the 3 kilogram object, plus the initial kinetic energy for the 7 kilogram object, plus the initial potential energy for the 3 kilogram object, plus the initial potential energy for the 7 kilogram object. There are no springs in this problem. Thank goodness, I can't imagine. Plus any work done on the system. And that equals the kinetic energy final for the 3, plus the kinetic energy final for the 7, plus the gravitational potential energy for the 3. Oh my God, so many variables, plus the potential energy due to gravity final for the 7. Now, if you're Physics 1, you know that we use KE instead of K, and we use PEG instead of UG, but it's the same thing, okay? All right, now you already have these skills, so you just go through and you say, is the 3 kilogram object moving in the beginning? Well, it doesn't mention initial velocity, so I'm going to assume that it's not moving, and neither of them are moving. If one's moving, they're both moving. If neither is at rest, sorry, if they're both at rest, if one's at rest, the other's at rest. Is the 3 kilograms above its height zero at the moment? No. Is the 7? Yes. Is there work done on the system? Yes, there's friction. We can see that right there. Is the system moving in the end? Yes. Is the 3 above height zero in the end? Yes. Is the 7 above height zero in the end? No, because it's going to be at height zero here. All right. Now it's just time to do what we do best, and that's called math. Don't tell the math teachers I said that. It doesn't make any sense. All right, so here we go. I would be doing, so there's going to be a lot of stuff going on here. 7 kilograms times 9.8 meters per second squared times a height of 0.5 meters. The work done by friction on an incline, as you know, is going to be negative all the time. Mu Fn, don't lose the distance. So it's going to be negative mu. Fn on an incline is mg cosine theta, and this is a 3 kilogram mass. Be careful here. It's a 3 kilogram mass, 9.8 meters per second squared. mg, sorry, I have to concentrate, cosine 40. Don't lose the distance. Now, the distance over which friction is acting is 0.5 meters. Okay, it is. It slides for 0.5 meters, and that will be the distance over which friction is acting. That's going to cause the system to, on the right, you have kinetic energy, so it's going to be moving. Now, if you want, you can combine their masses together because they're going to have the same final velocity. They're attached to the same string. So Vf squared, I usually just do it as 1. And then the final potential energy, sorry, I ran out of space, plus the 3 kilograms times 9.8 mgh, that is, times a height of 0.321 meters. Okay, so this is your work done. This is your kinetic energy. And this way over here is the final potential energy. And like you've done this so many times. Your next step, you know what to do. Please don't just go for an answer. You want to do each section individually. Like this is 34.3 joules minus the work done by friction, which if I was smart, I would have planned this out earlier and done these calculations for you. But now I'm just rambling while hitting a calculator. And who knows, if I make a mistake, that would suck to have to go back and do this whole thing again. So this would be 5 kilograms times final velocity squared plus mgh times 9.8 times 0.321. And we get 9.44 joules. All right, 4.3 minus 3.94 minus 9.44. So I get 20.9 joules equals 5 kilograms Vf squared. Solving for Vf, we get, let's hope, let's pray to the physics gods that I got it right, 2.04 meters per second. And is that the right answer? Come on, right answers. Yay! It's the little things in life. All right, so that's it. I mean, that's how you do multi-mass systems with energy. They're pretty simple, actually. I hope this seems much easier than the old way, which was FBDs and setting tensions equal. This is a welcome way to do it. All right, let's go back down to the bottom here, and we will discuss. I don't know why my computer's being stupid right now. I'm trying to scroll down, and it's like, no, you cannot. So here's the takeaways for this. First thing, I usually draw an arrow to show the direction of motion for each mass, and then I label a height 0. I mean, you saw me do that. You know, I showed where each mass would end. The 7 kilogram mass fell down, so I called its final position 0 because it was lower, and then for the 3 it was going to go up, so I called its initial position 0. And then once you do that, it's the same strategy as in the previous like work energy stuff, except that the work energy theorem should represent both objects. That means you have 2 kinetic energies, 2 potential energies for both initial and final. And you could see that right here. I mean, this is just one giant equation. Remember that if one is moving, the other is moving. If one is at rest, the other is at rest. So that kind of helps. And that's about it. There's not much more to say about this. If you're AP, odds are we'll get into some algebraic stuff where maybe we'll do some 3, 4, 5 triangles to make the algebraic stuff a little bit easier. But other than that, people, I hope you enjoyed this video. I mean, I thought it was absolutely fascinating, and the narrator's voice is just impeccable. So I'd give this puppy 3 out of 5 stars, and I would not change a thing.